Therefore, the ratio Q over V will remain a constant. Let's do another problem. If a parallel plate capacitor has a 0.15 millimeter separation, that is D, the plate separation, what must be its area for it to have a capacitance of 1 farad? You can see 1 farad is a very high value. B, if the plates are square, what is the length of their sides? Well, we are given the capacitance, you are given the plate separation, and you are not given a dielectric, which means we will use the value of kappa as 1, air capacitor. In a problem like this, if a dielectric is not mentioned, we will assume that it is an air capacitor and we use kappa equal to 1, dielectric constant as 1. So, we've got the capacitance of that capacitor is 1 farad. Epsilon naught is the usual value. The plate separation is 1.5 millimeter, which is 0.15 millimeter, which is 1.5 times 10 to the negative 4 meter. Well, kappa equal to 1. The capacitance of a parallel plate capacitor is kappa epsilon naught A over D. We know the capacitance, we know kappa, we know epsilon naught, we know D. Therefore, we solve for A. A equal to CD divided by K epsilon naught, and put in all the values. We got all those values there. C is 1, D is 1.5 times 10 to the 4, kappa is 1, and epsilon naught is 8.85 times 10 to the negative 12, and that area is 1.69 times 10 to the 7 meter square. It's a tremendous amount of area needed to build a capacitor of capacitance 1 farad in order to make so much a storage facility for large amount of charge. Well, if the plates are made of square, it's a square plate, what is the length and width of, or what's the length of one side? If this area is the area of a square, it will be length multiplied by length, is that right? If area is known, then that area will be equal to L squared for a square. That means L equal to square root of that area. And that means it is 4.11 times 10 to the 3 meter. Now, I included this problem just to impress upon you how big a plate is needed to produce a capacitor of capacitance 1 farad. Now, what is the length of that plate? 4.11 times 10 to the 3 meter is greater than 4 kilometers. So you need a plate greater than 4 kilometers side on a rectangle, and you need 2 plates like that to produce a capacitor of capacitance 1 farad. So 1 farad is a tremendous capacitance. Most of the capacitors that we use in the lab will be much smaller than 1 farad. They will be measured. I will show you some capacitors in a short while as we go on. Okay, let's do another example. A parallel plate capacitor has a capacitance of 2 microfarad and a plate separation of 1.6 millimeter. What is the maximum potential difference between the plates such that dielectric breakdown of air between the plates does not occur? Well, what is the maximum electric field, or what is the electric field required to create that dielectric breakdown? It is 3 times 10 to the 6th. how much charge is stored at this maximum potential difference? What is the charge density on the plates? Well, here we will use information that we have actually obtained from previous lessons and couple it with the concept of capacitance. Alright, what is the first thing that we need to do? What is the maximum potential difference between the plates such that dielectric breakdown of the air between the plates does not occur? Can you think for a while and tell me, if I have two metal plates separated by a distance d, there is an electric field between the plates. That means there is a potential difference between the plates. What is the relation connecting the potential difference between the plates, the electric field between the plates, and the plate separation? Can you think of a relation that we did some time ago? Well, delta V equal to negative E times D. Is that right? Yes. E equal to negative delta V over delta X. That is a relation. We have been using that many times. So, pick the data. Capacitance of the capacitor is 2 times 10 to the negative 6 farad, 2 microfarad. Epsilon naught is the usual value. The plate separation is 1.6 millimeter, which is 1.6 times 10 to the negative 3 meter. And kappa for air is 1. For dielectric breakdown to occur, the electric field must be at least this. This is the minimum electric field required to produce dielectric breakdown. So this is the electric field. Now, here I have the situation. These are the capacitor plates. The plate separation is 1.6 meter. The electric field between the plates is 3 times 10 to the 6. If the electric field increases any further, there will be dielectric breakdown in between. Now, E equal to V over D. I have done away with the negative sign. You see that? There is no need for the negative sign. We only need the magnitude. So we have E equal to V over D, or V equal to E times D. Remember, this is the same relation we used earlier. E equal to delta V divided by delta X. E equal to potential difference divided by the plate separation. So V equal to E times D. And E is 3 times 10 to the 6. D is 1.6 times 10 to the negative 3. And that is 4,800 volts. So the maximum potential difference you can apply between the two plates without causing a dielectric breakdown is 4,800 volts. If you increase the potential difference from this value, the electric field will increase, and that will result in dielectric breakdown. And remember, the capacitance will no longer work if there is a dielectric breakdown. The space between the two plates must be an insulator for the capacitor to function normally. How much charge is stored at this maximum potential difference? Well, we know the capacitance, we know the potential difference. Well, do we need anything else to calculate the amount of charge? Q equal to CV. Is that right? Because the definition of C is C equal to Q over V. Therefore, C equal to Q over V. Therefore, Q equal to C times V. We got a C, 2 times 10 to the negative 6. We just calculated V, 4,800 volts. Therefore, the amount of charge on the capacitor at that time is 0.0096 coulombs. Again, you notice that a coulomb is a very large amount of charge. What is the charge density on the plate? Now, how do you find that? The charge density. Well, you know that E, the electric field between two parallel plates. Have you forgotten that? The electric field at any point between two parallel plates is sigma over epsilon naught. We know the electric field 3 times 10 to the power of 6. And of course we know epsilon naught. We know it every time. Therefore, sigma equal to E times epsilon naught. That is 3 times 10 to the 6 times epsilon naught gives you 2.66 times 10 to the 5 Newton per meter square. And that is the charge density on the plates. Well, let me ask you one thing. What is a capacitor used for? Think about that. I will try and show you a couple of capacitors and show you what it is used for. Have you thought about the